The day the sky fell. The Chicxulub asteroid that ended the age of dinosaurs 66 million years ago measured approximately 10 to 15 kilometers in diameter. If an object of similar size were to strike Earth today, the consequences would unfold with terrifying precision, following the immutable laws of physics that care nothing for the 8 billion human lives in their path. Before anything else, the story has to tip its hat to the elephant calmly sitting in the middle of the room chewing popcorn. Armageddon, the 1998 film that taught a generation to believe Earth could be saved by oil drillers, duct tape, and a nuclear bomb with feelings. In that version of reality, humanity spots a planet-killing asteroid and immediately decides the best use of its remaining time is to teach roughneck workers orbital mechanics before sending them to punch a space rock into submission. In the real universe, however, a Chicxulub-sized asteroid would not be impressed. You could detonate a nuclear bomb inside it, and the asteroid would barely notice, continuing its 20-kilometer-per-second sprint toward Earth, now glowing faintly with the smugness of having survived human optimism. There would be no heroic drilling, no last-minute sacrifice, just a very expensive flash, followed by the same unstoppable object doing what gravity told it to do. To the movie's credit, it gives humanity only 18 days to react, which sounds absurd until you realize it's not entirely impossible. Detection systems can miss big objects until they're uncomfortably close. Realistically, we'd probably have more warning, maybe months or years, but the ending wouldn't change much. 18 days or 18 months, the asteroid wouldn't care. The real drama wouldn't be explosions and Aerosmith, but quiet meetings, grim calculations, and the slow realization that some cosmic disasters are not action movie problems. In that version of the story, Earth doesn't need heroes. It needs luck. And sometimes, the universe simply doesn't offer any. The mathematics of annihilation. Consider the scenario. A carbonaceous asteroid 12 kilometers across, traveling at 20 kilometers per second, typical velocity for objects in Earth-crossing orbits. The kinetic energy alone would equal roughly 100 million megatons of TNT, or about 2 million times the energy of the largest nuclear weapon ever detonated. This is not speculation. This is simple physics. 1/2 mass times velocity squared. The impact location matters enormously. An ocean strike, statistically more likely given that water covers 71% of Earth's surface, would produce different immediate effects than a land impact, though the long-term consequences would be equally catastrophic. For this analysis, consider a Pacific Ocean impact, similar to what likely occurred 66 million years ago when the Chicxulub impactor struck the shallow seas covering what is now the Yucatan Peninsula. T0, the first seconds. The moment of impact would be unlike anything in human experience. The asteroid would punch through the atmosphere in less than 2 seconds, compressing the air ahead of it into a plasma sheath reaching temperatures of 20,000 degrees Celsius, hotter than the surface of the sun. This superheated air would radiate thermal energy in all directions at the speed of light. Upon striking the ocean, the asteroid wouldn't splash. At these velocities, water behaves like solid rock. The impact would instantly vaporize a column of seawater 5 kilometers deep and dozens of kilometers wide. The asteroid itself would vaporize completely, along with an equal mass of ocean water and seafloor rock. This vapor, heated to tens of thousands of degrees, would explode outward and upward. The impact would excavate a transient crater approximately 40 kilometers deep and 100 kilometers across in the first 10 seconds. For comparison, the deepest part of the ocean, the Mariana Trench, is only 11 kilometers deep. The fireball, a roiling sphere of vaporized rock, water, and asteroid material, would expand to 200 kilometers in diameter within the first minute. This fireball would be visible from space, a glowing wound on the planet's surface, brighter than the sun. The first hour, fire from above. The thermal radiation from the fireball would be the first killer. Light travels faster than shock waves, faster than tsunamis, faster than anything except the human capacity to understand, in a final instant, what is happening. Across the entire Pacific Rim, a region home to billions of people, the thermal pulse would arrive within seconds of impact. In cities 5,000 to 6,000 kilometers from ground zero, the radiant heat would be equivalent to standing a few meters from an open blast furnace. Exposed skin would blister and burn, clothing would ignite, wooden structures would burst into flame, forests would combust spontaneously. But the thermal pulse would be merely the opening act. The impact would generate seismic waves that would propagate through the Earth's crust at several kilometers per second. The resulting earthquake would measure magnitude 11 on the Richter scale, a full order of magnitude beyond the largest earthquake in recorded history. To understand what this means, each integer on the Richter scale represents a tenfold increase in amplitude and roughly 31 times more energy. A magnitude 11 earthquake would release approximately 1,000 times more energy than the 2011 Tohoku earthquake that devastated Japan. Every fault line on Earth would feel this shock wave. The San Andreas Fault would likely rupture along its entire length. Dormant volcanoes would awaken as the seismic waves destabilized magma chambers worldwide. The planet itself would ring like a bell struck by a cosmic hammer, with the vibrations detectable for weeks afterward. The walls of water. The displacement of trillions of tons of water would create a mega tsunami unlike anything in human history. The initial wave would stand approximately 1,500 meters tall, taller than the world's tallest buildings. This wall of water would radiate outward in all directions at speeds exceeding 900 kilometers per hour, the speed of a commercial jet aircraft. In deep ocean, the wave would travel at high speed, but with relatively low amplitude. As it approached shallow coastal waters, the wave would slow but grow dramatically in height. By the time it reached the coasts of South America, Asia, and North America, it would still tower 200 to 400 meters high, higher than a 100-story building. Coastal cities would have between 30 minutes and 3 hours of warning, depending on their distance from the impact site. This would be enough time to understand what was coming, but not nearly enough time for meaningful evacuation. The wave would sweep inland for dozens of kilometers, scouring everything to bedrock. River valleys would channel the water even further inland. Cities like Los Angeles, Tokyo, Sydney, Lima, and thousands of smaller coastal communities would be obliterated. Conservative estimates suggest that 40% of the world's population lives within 100 kilometers of a coast. Most of these people would die within the first 6 hours. The sky falls. Meanwhile, the impact would have ejected an estimated 1 trillion tons of material into ballistic trajectories. Some of this ejecta would achieve escape velocity and leave Earth entirely. Most would arc through space and re-enter the atmosphere within hours, distributed across the entire planet. This is where the true global catastrophe would begin. As billions of tons of debris re-entered the atmosphere simultaneously, The collective friction would heat the upper atmosphere to extreme temperatures. The sky itself would glow red, then white hot. The thermal radiation reaching the surface would be equivalent to the heat inside an industrial oven, approximately 400 degrees Celsius or 752 degrees Fahrenheit. This global thermal pulse would last for several hours. Any organism exposed to the open sky would be baked alive. Forests would ignite spontaneously on every continent. Grasslands would become infernos. Animals would suffocate as the fires consumed oxygen and produced toxic gases. Studies of the Chicxulub impact suggest that approximately 70 to 80% of Earth's forests would burn in this initial conflagration. The fires would be unlike anything in human experience. They would burn simultaneously across North America, South America, Europe, Asia, Africa, and Australia. The smoke would be visible from space, a dark shroud spreading across the planet. In some regions, the fires would burn for weeks, consuming everything combustible. The long dark. When the fires finally exhausted themselves, they would leave behind a planet transformed. The smoke and soot from burning forests, combined with the pulverized rock dust suspended in the stratosphere, would create an aerosol layer that would block approximately 99% of sunlight from reaching the surface. Without sunlight, surface temperatures would plummet. Climate models suggest a global average temperature drop of 20 to 30 degrees Celsius within the first few weeks, with some regions experiencing drops of 40 degrees or more. Snow would fall in tropical regions. The oceans, still retaining some heat, would steam in the frigid air, creating perpetual fog and adding to the darkness. Photosynthesis would cease. This is the mechanism that would ultimately cause the mass extinction. Plants require sunlight to produce energy. Without it, they would die within weeks or months, depending on the species. The collapse of plant life would trigger a cascade up the food chain. Herbivores would starve. Carnivores would follow. The fossil record from the Chicxulub impact shows that approximately 75% of all species went extinct, and the same percentage would likely apply to a modern impact. The impact of winter would last for years. Current models suggest anywhere from 2 to 5 years before enough dust settled for significant sunlight to return. During this time, surface temperatures would remain well below freezing even at the equator. The growing season would be reduced to zero. Agriculture would be impossible. The ocean dies. The marine environment would face its own apocalypse. The impact would acidify vast regions of the ocean with vaporized rock, creating conditions lethal to most marine life. The mega tsunamis would stir up sediments and mix ocean layers, disrupting the thermohaline circulation that drives ocean currents. This circulation, which includes the Gulf Stream and other major currents, regulates global climate and distributes nutrients throughout the ocean. Its disruption would have cascading effects lasting centuries. Most critically, the darkness would kill phytoplankton, the microscopic organisms that form the base of the marine food chain and produce approximately 50% of Earth's oxygen. Without sunlight, phytoplankton would die within weeks. The die-off would propagate up the food chain. Zooplankton, small fish, large fish, and marine mammals. The ocean would become a vast graveyard. Approximately 50% of marine species are going extinct. However, the modern ocean is already stressed by overfishing, pollution, and climate change. A Chicxulub-scale impact today might produce even higher marine extinction rates. Humanity's fate. The human species would face extinction-level conditions. Of the 8 billion people alive at the time of impact, the vast majority would die within the first year. The initial casualties from the thermal pulse, tsunamis, and earthquakes would number in the billions. The subsequent starvation as food supplies ran out would claim billions more. Modern human civilization is utterly dependent on agriculture, which requires sunlight, moderate temperatures, and a growing season. None of these would exist during the impact winter. Stored food supplies would sustain some populations for months, but not years. Hunting and foraging would become impossible as animal populations collapsed and plant life died. The survivors would be those with access to deep shelters, stored food, and the means to generate heat and light without sunlight. Military bunkers, deep mines, and specially prepared survival facilities might shelter thousands or tens of thousands. But even these refuges would face severe challenges. Ventilation systems would need to filter toxic air. Food would need to be rationed carefully. Social cohesion would be tested as resources dwindled. Optimistic estimates suggest that perhaps 0.01% of the human population might survive the first 5 years, roughly 800,000 people, scattered across the globe in isolated pockets. These survivors would emerge to find a planet utterly transformed, a frozen wasteland where summer temperatures barely rose above freezing, where most familiar plants and animals had vanished, where the air was still hazy with suspended particles. Recovery. Deep time. The Earth would recover, as it did after the Chicxulub impact. The geological record shows that it took approximately 30,000 years for biodiversity to begin recovering after that ancient catastrophe, and roughly 10 million years for biodiversity to return to pre-impact levels. The survivors would be small, adaptable species. Rodents, with their ability to shelter underground and survive on minimal food, would likely persist. Some birds, particularly scavengers, would find ample food in the billions of corpses. Insects, with their short generation times and ability to enter dormancy, would prove remarkably resilient. In the oceans, deep-sea organisms that don't depend on photosynthesis would survive, along with some fish species adapted to extreme conditions. For humanity, recovery would be measured in generations. The survivors would need to relearn agriculture in a changed climate, hunt the few remaining animals, and rebuild technology from salvaged materials. The knowledge accumulated over millennia, stored in books, computers, and human minds, would be the species' most valuable resource. But much would be lost. The complex global civilization that existed before impact, with its cities and industries and billions of people, would be gone forever. The probability. This scenario is not mere speculation. An asteroid the size of Chicxulub strikes Earth, on average, every 100 million years. The last one hit 66 million years ago. Statistically, we're not overdue. Probability doesn't work that way. But the risk is real and ongoing. Current surveys have identified approximately 90% of near-Earth asteroids larger than 1 kilometer in diameter, and none pose a threat for at least the next century. But the surveys are not complete, and objects can approach from directions that make them difficult to detect until it's too late. The Chicxulub asteroid likely approached from the direction of the Sun, hidden in the glare until the final weeks or days. The scenario described here is what would happen, not what will happen. But the laws of physics that would govern such an impact are immutable. The energy calculations are straightforward. The cascade of consequences, thermal pulse, mega tsunamis, impact winter, mass extinction, follows inevitably from the initial conditions. 66 million years ago, the dinosaurs had no warning and no means to prevent their extinction. Humanity has both the technology to detect threatening asteroids decades in advance and, potentially, the capability to deflect them. Whether we will maintain and improve these capabilities, whether we will take the threat seriously enough to invest in planetary defense, remains to be seen. The mountain-sized rocks are still out there, orbiting the sun, following their ancient paths through space. Someday, one of them will have Earth's name on it. The only question is whether humanity will be ready.